Okay, hello everybody. My name is Paavo Alku, and I'm going to give a talk entitled Glottal Inverse Filtering Analysis of the Voice Source Methods and Utilization in Classification of Speech and Voice Disorders. And my apologies that I was not able to attend the conference in person. So this is the contents of my talk. I start with a short introduction, then I talk a few words about the Glottal Inverse Filtering methods and glottal parameters. The main part of my talk is sections 4 and 5, where I explain how we have used inverse filtering, glottal parameters in classification, machine-based classification of disorders from speech signal. And I end my talk with a summary and conclusions. By the way, I will use the word speech rather than the word voice throughout my talk, even though I consider these two, or because I consider them synonymous. So let's start from the introduction to inverse filtering. So inverse filtering is an old technique to analyze production of speech and voice signals, and that's based on simplified assumption of voice production called source filter model. And according to that model, speech production can be assumed to happen as a result of three processes which are shown in this picture. So we have the excitation, which is the flow of air through the vibrating vocal folds. We have a filter, which is a very strong physiological filter called vocal tract. And the third process is called lip radiation, which corresponds to conversion from the flow at the lips into the pressure signal, which is captured by the microphone. So throughout my talk, we will use the so-called free field microphone recordings as an input to our inverse filtering. And the idea of inverse filtering the idea itself is quite simple and can be explained in frequency domain using this kind of little bit messy picture. So inverse filtering is actually or can be considered as a computer program which tries to estimate from a given speech signal this first process, the glottal excitation, by estimating this second and third one. And the third one, the lip radiation, is considered to be a very simple high-pass filtering. So the main problem is to estimate the vocal tract. And if we are able to estimate, form a mathematical model for the vocal tract, which typically is some kind of digital filter, which have a nice kind of spectrum, which is shown here in the upper left-hand side of the picture. The inverse filtering corresponds to cancelling the effect of that physiological vocal tract filter by filtering the recorded speech through the inverse of the vocal tract model and through the inverse of the lip radiation effect. And we end up having an estimate for the flow of air through the vocal folds, which served as excitation. So that's what the inverse filtering is about. And it's worth observing that in our study, as I mentioned, we use the microphone signal as the input. It is also possible to use so-called flow mask recordings based on Martin Rosenberg studies, and these kind of inverse filtering has been widely used, for instance, by Johan Sundberg and other ones. The reason why we are not using them in this talk is that we are interested in biomarking studies where speech needs to be recorded as part of our everyday life. So we cannot use mask recordings for this kind of applications. Inverse filtering in general has both benefits and drawbacks. Benefits are obviously that it is non-invasive technique. It gives valuable information about the production of speech in the form of a real phenomenon. That means the flow of air through the vocal folds. And it can be used in a range of technical applications in biomarking and speech synthesis. However, the inverse filtering also have drawbacks. The accuracy, especially for high-pitch speech, is not very good. In most of the cases, some techniques call for user-based adjustments of the vocal tract under resonances that might bias the estimate result by the assumptions of the experimenter. We need typically high-quality recording equipment, and we had to keep in mind that the reality in voice production system is nonlinear. However, large part of the inverse filtering techniques are simple linear systems, so we cannot model in detail nonlinear phenomenon with linear techniques. However, this doesn't mean, in my opinion, that we cannot use linear techniques at all, despite the reality is nonlinear. So if, for instance, we consider this well-known interaction between the source and tracked, if that is created by the laws of Mother Nature, and that happens in real speech production, we can still, in my opinion, use linear methods to estimate the source, but we have to keep in mind that that will always be the interactive flow what we are then estimating. Inverse filtering analysis in general can be divided into two phases. The first phase is the inverse filtering itself, where we have typically a wide range of speech utterances, and then these will be inverse filters. And the result will be time domain estimates for every speech sample. That means that typically have a lot of data after inverse filtering. Therefore, we typically in all the studies, I would say, need some kind of parameterization stage where we used pre-selected good numerical values to extract the most important information out of those waveforms. So that second stage is called parameterization. So a few words about the inverse filtering techniques. I'm not going into any details. However, I want to point out that this is a quite old area of technology. The first studies were published the end of 1950s. The 1960s, very important research was conducted at KTH by Gunnar Fant and other famous researchers, Martin Rodenbergs and others. Starting from the 1970s, people moved, of course, to digital techniques. And on this page, you can see a whole lot of different papers referred. So this is just part of those articles which have been published since the early 70s. So what is the main message of this page is to say that, well, there are existing old techniques and some very recent ones which have been developed, for instance, last year. We could classify inverse filtering techniques into different categories based on a few attributes. So I mentioned here so those attributes which I by myself typically use when I categorize different techniques, inverse filtering techniques. So first thing is that there are techniques which are based on free field microphone recordings, which is the case of this talk, and then there are techniques based on this Rodenberg's mask. So that's one attribute which separates techniques into two parts, even though the same algorithms can be used. Inverse filtering techniques are different depending on what kind of evaluation criterion is used. I mean, subjective versus objective. So in my team, we mainly use in objective methods. Inverse filtering techniques, some of them are linear, whereas there are also non-linear techniques. And then related to modeling of the vocal tract, inverse filtering techniques can be separated to those which are based on so-called autoregressive models, which are very widely used. And then there are different techniques which are based on stage-based modeling and Kalman filtering, for instance. So let's look at a little bit more in detail into one specific technique. And not surprisingly, this technique was developed by one of my students. So this is just an example of technique which we use at the moment when we are conducting inverse filtering. So the technique is called closed phase analysis, QCP. And from the point of view of those four attributes which I mentioned, so this technique uses free field recording. It's automatic. It's based on linear modeling, and it's based on autoregressive mathematical modeling of the vocal tract. And how inverse filtering is computed by these techniques, I'd like to explain this a little bit further in order to clarify how inverse filtering can be how separation of the source and tract happens in one inverse filtering technique. So I want to emphasize this is just one way to make this separation. So the starting point is a recorded speech signal. For instance, in this slide, the upper picture shows a 40 millisecond section of voice speech vowel sound. And the lower one, that is one of the key functions in our methods called temporal weighting function. That is a positive time domain function which is equal to unity most of the time. However, it goes down to a small value in the vicinity of glottal closure instance, which happens somewhere here. And so by my mouse here. Okay. And the reason why we compute this temporal weighting function is that we can use that in a very nice manner inside the mathematical optimization in the computation of the vocal tract in that autoregressive model computation. And using this simple weighting function, we kind of tell to the mathematics that those sections of the sound which take place in the vicinity of the glottal closure instance are very much affected by the source, not by the tract, because there's a very abrupt high energy excitation coming from the vocal tracts, from the vocal folds at those instants. So we are not definitely multiplying these two waveforms, but we are using this weighting function to weight the error in such a manner that it takes into account better the response of the tract rather than the energy coming from the source. So we are modeling the tract, we want to get rid of the source. Okay, and this mathematics can be very easily optimized. We end up having this kind of optimization result. And then we obtained a digital filter which models the vocal tract, and we can cancel the effect of that from the speech signal. This is one result which I obtained from my speech signal. So this is now the estimate of the flow of air through my vocal folds as a function of time. There's no absolute flow values here available, but we can obtain the shape of the waveform quite easily. Okay, then a few words about the second stage of the glottal source analysis. So we now know something about the inverse filtering. There are different methods. Some of them are automatic, some of them not, and so forth. Then we end up having lots of estimated time domain waveforms. So now we need to select key numerical values to extract the best possible information out of these waveforms. And these values can be then used in ordinary, let's say, fundamental research, or they can be used together with machine learning for this biomarking applications. And again, I just want to point out that during the past decades, there have been several papers published in this area, and lots of different parameterization methods have been proposed, both in the time domain and in the frequency domain. Just to give one example, this is a classical time domain parameter called closing quotient, which means that if my inverse filtering stage have given me a very nice looking glottal waveform, I simply compute this time length of the closing phase, and I compute the ratio of that over the ratio of the fundamental period. And that gives me one numerical value to describe the whole long waveform, or actually over one glottal cycle. It's also possible to convert the time domain waveforms into frequency domain and measure the most obvious frequency domain effect, and which is the spectral tilt, by, for instance, measuring the dB ratio between the level of the fundamental and the second harmony. And there are a range of different parameters like this. Okay, now we know something about the inverse filtering technique, and we know something about the parameters. These are all quite established old techniques. However, new inverse filtering techniques pop out every year. Now we move slightly to this area, which is kind of main part of my talk. So can we use inverse filtering and glottal source parameters for biomarking studies of human health? And before understanding that, I will describe you next in this section number 4, what kind of systems are currently used, what kind of machine learning systems are currently used for this biomarking. So I call this area of science as speech-based biomarking of state of health. So this refers to signal processing and machine learning studies which aim at automatically biomarking or predicting the state of health of a talker based only on the speech recording of that person. And the underlying reason is understandable because we all understand that speech signal is a unique signal. It's produced by a physiological system. And if there's something wrong with any of those organs which are producing that sound, then tiny little so-called extralinguistic cues will be embedded in the outcoming speech signal. Now the problem is that could we use deep learning, machine learning, signal processing to predict the state of health of this talker based on this acoustical speech signal? And in general, I would like to emphasize that this research area has becoming of very great importance in speech technology, and there are a few kind of justifications which have made it so popular nowadays. The one thing is that most of the people talk on a daily basis, so we use speech as everyday life. The second thing is that nowadays very large part of the people around the world have some kind of equipment like mobile phone, laptop, which enables recording the speech signal easily as part of our everyday life. So when we put these two things together, we can understand, we can argue at least, that speech actually constitutes a very effective and attractive biochannel to biomark the health state of a very large number of people around the world. And this analysis can benefit from being non-invasive. It can be, in principle, conducted outside the hospital, and it can be conducted even before the person himself realizes that there's something wrong with the health. And what is very important, this is something which I emphasize to my students, that we should not advertise this area of research to be a replacement for true clinical examinations. But instead, its main function is to provide preventive healthcare technology, which could enable early detection of some diseases before the person himself realizes that, well, it's time to go to the hospital. So there are obvious justifications why which makes this area worth studying and very important. And of course, we have a number of very good deep learning techniques available at the moment. If you look at this problem from the point of view of machine learning, there are typically a couple of sort of major problems which are studied in research. The most typical and widely studied problem is the so-called binary classification problem. And this refers to a problem where we have two classes of people. For instance, those who are healthy and those who suffer from COVID-19. And the idea of the machine would be to automatically distinguish these two classes from each other based solely only on the speech signal of the underlying person. The second problem, which is not that much studied, but which is very important as well, is multi-class classification, where instead of having just healthy versus COVID-19, for instance, you might have 3 or 4 diseases and the healthy ones, and the machine needs to distinguish a number of different diseases based on speech signal. Or as an alternative, you might still have just one disease, for instance, Parkinson's disease, and the goal of the machine would be to distinguish whether a person has a mild class of severity or mediocre level of severity or high severity level. So these are examples of studies which are conducted. So in my talk, I will only address this first problem, which is this binary classification problem. So what kind of techniques are can be used at the moment in this area. So they can be separated, in my opinion, into two parts. The first part is so-called classical pipeline approaches, and the second one is a little bit more modern, that's called end-to-end system. But let's first try to understand what is the classical pipeline system. So classical pipeline system, if you want to build a system where the computer automatically, for instance, detects whether the person is healthy or has a COVID-19. If you end up using the classical pipeline system, you are building a system which has two separate stages. The first stage is so-called feature extraction stage, where speech is converted to very good features. For instance, glottal features, but there are, of course, other features which may have been mainly used. I will come back to this question later. And the key of that system is the next block, which is called classifier. Okay, we have two parts, the feature extraction and the classifier. And what kind of classifiers are used? So I just like to very shortly explain one of the most effective classifier which has been used in this domain, and that's called SVM, support vector classifier. The idea of the SVM classifier, if I want to explain that very easily, shortly, is that let's assume that we have 8 speech samples, for instance, vowels, which have been produced by some pathology, whatever that pathology is. And then we have 8 speech samples which have been produced by healthy talkers. And we express all these speech utterances in a very low dimensional space, which is spanned by 2 acoustical features, so x1, x2. To put it simple, x1 could be, for instance, f0, and x2 could be f1, first format, whatever. So these are just 2 acoustical parameters, a very simple 2-dimensional space. In this simplified example, these pathological samples happen to be on the upper left part of the space, and these healthy samples happen to be located in the lower right part of the space. The SVM is a classifier, which in the training phase, that means we are given both these black ones and these white ones. We have access to both of them, and SVM simply finds an optimal separation between these 2 classes by searching for a so-called subspace, which in the case of 2-dimensional space is simple, a linear line, which separates by a largest margin these 2 classes. That means this red line can be defined when I'm given these 2 classes, samples in 2 classes. You can also see this green and blue line here, and these are, as you can see, non-optimal lines. They are not computed by SVM. But to put it simple, we are in a training phase. The SVM finds this optimal red line, and that's what the classifier, that's when the classifier is then trained. And then when you have a testing sample, it is now either healthy one or pathological. It drops to either left or right side of this red line. And if it's on the left side, then the machine makes a decision that this must be a pathological sample because it was on the left side of the train subspace. Okay, and the same holds true if it's on the right hand side, then it's considered to be healthy. So this is the way it works, to put it very simple. Of course, there are lots of other details, but that's the way the classifier works. We need a training phase to define these decision boundaries, and once that is done, then you can use that technique in the testing or evaluation part. And typically the systems look like this. So the system, when it's built, is shown in this lower part. We have a speech signal coming from microphone. We extract features, and then this classifier makes the decision whether the signal was healthy or pathological. And as I explained here, before we can use it, we train the classifier, and we need speech training data where somebody has labeled the data to be either pathological or healthy. So that's very simple. And again, we need two phases, the feature extraction and the classifier. And this technique is widely used still today. It benefits from being a good classifier, especially in the case when there's a little amount of training data available. And this is one example from our study where we use this SVM type of classifier. We don't see, this picture here shows two-dimensional space where we have two types of speech samples. The crosses refer to speech samples which were recorded from dysarthria patients suffering from a severe level of the disease, and these black dots refer to patients whose severity was less severe. And in this case, we used two Glottal parameters, and we were able to show a very nice separation of the two classes. And if we had this kind of data, the SVM training would be very easily be able to make a quite good separation of the two. So I will come back to these Glottal parameters later. As an alternative to this classical pipeline system, which is shown here at the lower part of the picture, if you look at the literature, what's happening today, so people are increasingly using, researchers are increasingly using deep learning techniques. And therefore, the alternative to this classical pipeline system, so-called end-to-end system, has become very popular nowadays. And this picture here describes a typical end-to-end system. So what is a major difference between this one and the previous one is that we don't have a separate feature extraction and classifier here, but we have one large bulk of neural nets between the input and output. And the neural net kind of inherently solves the features and the classification. Right. So the input to the system is either the microphone signal, it's in the time domain, or it is very often converted to a spectrogram, which is the case of this picture here. So this is the input, and if you look at the output, so this is the output which you want to get. We are talking about the binary classification. The machine needs to automatically make a decision whether this speech sound belongs to a healthy population or to some pathology. And what happens in between is a bit complicated stuff. I'd like to explain the main parts of that. So this kind of end-to-end system consists of neural nets, which are typically using so-called CNN networks, convolutional neural nets. And convolutional neural nets are typically in layers of several CNN sort of layers. And what CNN actually does, it takes the input, which is in this case kind of image of a voice, a spectrogram. So in this picture, I have now shown this spectrogram as a matrix where you can see that this is a frequency and this is time and whatever, and these numbers here corresponds to the color code of this input signal. And what is the key thing is that in this convolutional neural net, we filter that input signal several times with a parameter which is called the filter or kernel. And that is a most important parameter which we want to solve. And thus filtering happens that this filter matrix kind of slides over this input signal, and it multiplies and adds to input signal to get an output. And this output is then very importantly matched by a predefined so-called activation function, which needs to be a nonlinear function. Okay, so this is a question having several times of filtering with this kind of sliding windows. And in addition, we need to have so-called pooling layers to lower the dimension. And at the end, we have another neural net. And then at the final end, we have this, what we are interested, the binary decision. Okay, and the whole thing happens in such a manner that we start with the random values of those parameters, for instance. The network has huge amounts of parameters, and luckily we have access to labeled data. That means we have a whole lot of different speech signals, and somebody has labeled this is healthy, this is pathological. And then these network parameters are iteratively updated based on so-called loss function, which is mathematically called binary cross-entropic loss function, in order to improve and improve this decision based on the label, which is known to the system. And this happens in the training phase, right? So it's cause for iteratively updating the filter parameters of these convolutional layers and then these final layers here. And once the system has been trained, then we simply take the test signal, convert that to spectrogram, and that is filtered by a trained network, which then gives the output, the probability whether this input was healthy or pathological. So that's the way it happens. It's a very effective technique. It gives good accuracy. However, it unfortunately typically calls large amounts of training data. And this is one of the key problems in our study area, that we unfortunately don't have access to large amounts of training data. And therefore, these classical pipeline systems might still be more attractive or better systems nowadays. But for instance, in my team and a number of other research teams which are using these techniques, we use both of them. And we typically compare these classical pipeline systems to these modern end-to-end systems in our work. And the problem, as I already told, for these end-to-end systems are that they are not only dependent on they call for a large amount of training data, but the issue which I'm personally very much not happy with is that they are very effective techniques, but they only give the decision, okay, the input signal was pathological or it was healthy. But clinicians and researchers might be more interested in understanding why this happened. So therefore, I still personally think that this feature extraction should not be forgotten, because it tells quite often very much more informative information, gives much more informative knowledge about the underlying reasons why a certain speech signal was considered to be healthy and versus pathological. Okay, so that was, now we know something about the inverse filtering parameters, and then something very general about the biomarking. And biomarking networks can be constructed based on classical pipeline systems where you have a separate feature extraction and classifiers, or as a complete end-to-end system. And both of them need training data. Both of them aim to conduct automatic detection for the input signal by the machine. And we are talking about the binary decision, healthy versus pathological. How can these two issues be combined? And the two issues are inverse filtering and its parameters, and then this machine learning part. So in my team has, during the past years, and also other teams, we have done a number of different studies where we have kind of taken advantage of this a little bit more basic research-oriented inverse filtering and voice source parameters, and combined them with this modern machine learning-based biomarking studies. And on this page, you have seen some of the articles which have been published in this area, not in our team alone, but also by other teams. And in this chapter number 1, section number 5, I will now describe a few example studies which have been conducted in my team on this topic. So we have combined inverse filtering and Glottal source parameters and machine learning biomarking studies in these examples. So the first study was published a couple of years ago by my team. And in this study, we were interested in using inverse filtering Glottal source parameters to automatically separate healthy speech from speech which has been produced by patients suffering from heart failure. So when we are talking about biomarking, we typically talk about Parkinson's disease or voice problems, voice disorders, but it's worth understanding that also disorders like heart failure could, in principle, be detected. And that's something which we were interested. We recorded a small database in Helsinki, 20 heart failure patients in hospital, 25 healthy controls, and we constructed a pipeline system. And then we were interested, okay, could Glottal source features help in this detection task? And here you can see some examples of the waveforms which kind of make us to study this question. The 4 panels are shown in such order that the first panel is the microphone signal of a healthy talker, a male talker. The second one is the estimated glottal waveform of that talk. Panel number, third panel, which is here, shown here, is the microphone signal of a heart failure patient, and the lowest one is the estimated glottal flow of that patient. So what we can see by comparing these two curves in general is that there seems to be a difference between the glottal source waveform between at least these two representative subjects which belong to different classes. The healthy one shows a clear closed phase, whereas that is not obviously shown by the patient. So we built this kind of classical pipeline system. Again, this is the pipeline, microphone signal, features extracted, SVM classifier train or different classifiers. And what was our special goal here is that we use glottal features and then some other speech features here to see whether glottal features bring some additional information. And this is one boring table of that study, a bit complicated one, sorry about that, but what is shown here is that we had 4 different classifiers. So these are the machine learning heart of the system, and they can be implemented in different ways. So SVM is obviously the typical reference system, and then we compared a wide range of different features by using feature selection. And what is shown by these red circles here is that the overall result was that the baseline system, which widely used MFCC features and SVM classifier, the performance improved by 5 percentage units when we added these glottal source features. And this kind of result has been replicated in several of our recent studies. I will come back to this later, but this is just one example that what kind of results we have been doing. There's certain disorder, we have a recorded speech data, and then we build classifiers. Most likely we try glottal features, and then we evaluate the system using this kind of metrics. And at least in this case, it means that the automatic system gives a better accuracy when glottal features are used. Another study was published a year earlier. We have a number of studies, and just mentioned shortly that here we used an existing database on children's speech and children suffering from specific language impairment. I just want to mention this study because our results and also other researchers who have been using this existing database have managed to show extremely large accuracy. And just want to remind that the question that what is a good accuracy is a very difficult problem, because that depends, of course, very much on the data itself. So for this database, we were able to show a very good accuracy, close to 100%. That means the machine almost perfectly makes the decision. But the underlying reason was very much based on the fact that there was a very large difference between the healthy sounds and the pathological ones, which were very pathological. Let's take a third example of our studies, and this was published again 3 years ago, and this was a little bit more complicated study because we compared different dimensions of the study area. We first of all used different databases, all which were partly related to dysarthria and dysphonia. And then we were investigated again whether glottal source features help for this kind of detection problems. But we were also interested to use these glottal source features for not only for the classical pipeline approach, but also for the end-to-end system. And let's look at what we built in this system. So again, this classical pipeline system, as shown in a couple of previous slides, is the one where we have speech signal, feature extraction, and then SVM classifier. And the binary output is one which we are interested in. And the system is trained using these existing databases, and we use widely used reference features called OpenSmile features, which have been used in a very large number of similar papers. And then we added these inverse filtering based features. And in the end-to-end system, this is now something a little bit more complicated. We use the speech signal as an input, which is supposed to be used as a default input in end-to-end systems. But this is a very rare study in the sense that we also use the inverse filtered glottal waveform as an input. And we were interested to see that, okay, could glottal wave inverse filter be used to provide kind of alternative input to these CNN-based networks for the detection task? And what are the results? My apologies that this is a very big table, but let's try to see the forest for the trees. What is shown in this table are these 3 dimensions which we have studied. So we have 3 databases which are given here: UA speech, Togo, and UPM database. So these 2 databases are on dysarthria, this is on dysphonia. And then we have metrics: accuracy, sensitivity, specificity. It's very easy to understand that if those numbers were 100% in all of them, then we would have a perfect system. So the closer to 100 this metrics is, the better the system. Okay, and then we have a wide range of different features which were very interesting, and these results are all based on this classical pipeline systems which are shown here. So the feature extraction plus SVM. And what is our overall observation is that every time when we combine these glottal features to these existing features, we end up having a very good, we end up having the best accuracy compared to these existing networks. And this is the results which we have observed in several studies, and it's worth emphasizing that glottal features by themselves typically don't give the best results. The existing database features give typically something which is a little bit better. But when we combine these glottal features into the existing large feature sets, then these glottal features, which are based on inverse filtering, they seem to give some kind of supplementary information to the system, which helps the system to give better results. So this is kind of overall results we obtained from here. And then interestingly, let's look at what happened for this end-to-end system. So again, the end-to-end system doesn't need any features. We have a speech signal, which is the default assumption, or in this case, we use the inverse filtered glottal waveform as an input. And what we were surprisingly able to show that for these three databases, the glottal waveform input gave, in most of the cases, a better accuracy compared to the speech signal itself. So what this means, in my opinion, is that given the fact that the end-to-end system have a huge number of different parameters and the amount of training data is still quite small. So it helps the training of the system by converting the very complicated speech pressure signal in the more kind of simple elementary type of waveform, which is the glottal source. And when that signal is used as the input, the system sees to perform better. However, if we had a large amount of data, then we wouldn't most likely end up having this kind of difference. So I think that we have come to the final section of my talk. Glottal inverse filtering technique is an old technique which benefits from being a non-invasive tool which can be used to estimate the excitation of voice speech from microphone recordings. And many inverse filtering techniques have been developed and many glottal parameters have been developed based on different ideas. However, this development is interestingly going on, and these deep learning techniques are hopefully also being used in this area in the future. And this inverse filtering has been classically used in fundamental research, but it has been a topic of interest for some research teams recently working on slightly different approaches. And this different approach is this biomarking of the state of health from speech. And that calls for combining inverse filtering with machine learning. And the benefits of these techniques are very attractive, namely we can record speech easily in everyday life with phones, and this technique should be seen as a preventive healthcare technology, and that is one application for inverse filtering and glottal source parameters. It is possible to use inverse filtering with machine learning networks which are based on classical pipeline systems, and also use that in end-to-end systems. Our overall results have shown that these glottal source features, when we are interested in different, when we have been doing different, working with different disorders, they as such are not the best possible features. However, when we combine them with some existing widely used features like open smart features, MFCCs, and so forth. So in the almost all experiments when we have computed or published, we have shown that okay, the accuracy of the system improves by adding these source-related features. So that means that these existing data features don't take into account the role of the glottal source as properly as inverse filtering takes that into account. I would also like to emphasize that currently our research area interest in speech technology in general seems to be going towards deeper and deeper models and using so-called artificial intelligence and deep learning in general. And that has, in very many studies, been reflected by showing that, okay, it helps to get a better performance of the system. However, I would like to kind of defend the role of speech features, and glottal features in particular, not only as a kind of technical ways to conduct this detection task, but also as a method to help the clinician or the researcher to extract knowledge from the speech signal, a voice signal. So I'm a little bit confused by a number of papers where people seems to be interested on the kind of black box type of system, which is trained to be better and better using and deeper models. But the clinician most likely is also interested in why this automatic detection happens. And then to answer that question, I still think that features can be used effectively. They can be used better to visualize why certain things happen. And then finally, I think that in the future, in the area of glottal inverse filtering, we definitely need more open access tools. My team has developed some of them, not recently, but that is something which definitely is needed. I didn't address that at all in my talk. And in the area of biomarking, I think that these glottal source features have something to give. They are not a miracle, but they help. And then we, of course, have this basic problem that we are developing inverse filtering. We should need the ground truth, and that is problematic. So we need a better ways to evaluate inverse filtering algorithms. And yes, I think that was everything I wanted to say, and I thank you for this opportunity to give this modest talk, and I look forward to your questions in that part of the conference. Okay, thank you.